Hello, hello, hello. This is Nicholas, and I'm doing a second video on a continuation of my Laplace transforms, and I'm gonna be deriving some basic Laplace transforms that you really just kind of need to know, and also proving the existence of the Laplace transform. So let's start with the existence. So if we have a function, say f of t, and we say it's piecewise is the word they use, piecewise continuous on 0 to infinity. And what I mean by piecewise continuous is it's continuous and it only has a finitely many number of jumps in it. In other words, maybe here's our function. Maybe it's here, goes like that, open circle, we close circle. There's an open circle, and then maybe it close like this, and then it goes up like that. So let's call this point x0 and this point x1. Then we would say at x0 and x1 there's a jump there, or not a removable discontinuity. I just like the word jump. So if it has a finitely many number of those on the interval from 0 to infinity, then we say that it's piecewise continuous. F of t is piecewise continuous. And it has this thing called exponential order. And I'm going to use the variable alpha, exponential order alpha. Then the Laplace transform of f of t exists for s being greater than alpha. So let me just talk about exponential order real quick. That is just basically your function is bound below by some other exponential function in the form of e to the some constant times x. So say for what the hectagon? So say for example we have e to the 2t times the sine of 2t. This has exponential order alpha equal to 2 because the function sine of 2t is at most 1. So this whole function is at most e to the 2t. So we can say that it is at most e to the 2t times some constant. They use the word, they use the letter m as the constant there. So that's what we mean by exponential order. The function e to the t squared, for example, does not have exponential order because it is it's increasing quicker than any other exponential function in the form e to the cx, m e to the cx. And we can show that because the limit as t approaches infinity of e to the t squared over e to the cx is infinity. So how will I prove this existence? Let me see. So the Laplace transform of f of t is the integral from 0 to infinity of f of t times e to the negative st dt by definition. I can split up this integral into two parts and partition it at, say, an x value of t. So we still have the same thing that we're integrating. And now this goes from t to infinity. And so what we can do is we just have to show that each one of these integrals don't diverge, and then that would mean that the Laplace transform of f of t would be existent. So this first integral here, it should be pretty obvious that this integral here exists because well, we're assuming f of t to be piecewise continuous, so there's nothing wacky with continuity going on, and e to the negative st decreases in area below its curve as t gets bigger. So that integral, that first integral, exists. It does not diverge. Now this second integral here, what I can use to show its convergence to some value is an integral comparison test, similar to how you did a series comparison test maybe in Calc 2. Since we assume the function f of t has exponential order alpha, then what we can say is that the integral from t to infinity of e to the negative st times f of t dt, it's got to be, by the definition of exponential order, it's got to be less than m times the integral from t to infinity of e to the negative of s minus alpha t dt. So what did I do there? I just replaced f of t with, f of t, technically the absolute value of f of t, has to be less than m e to the alpha t. That's the formal definition of exponential order alpha. So I replaced the f of t with m e to the at, or in other words, me. And then I just use exponent properties. So this integral here just becomes m e to the negative of s minus alpha t over s minus alpha. And this, as when we plug in this t here, that's just a number. And when we plug in infinity, it's definitely not going to go off to infinity because we have this negative sign here. That's why I wrote it that way. So in other words, this is going to be less than infinity. So both of the integrals, the first circled integral and this integral, converge. And therefore the Laplace transform exists, given these two initial conditions. So now let's do some basic Laplace transforms. Let's do the Laplace transform of a constant, c. That's c times the Laplace transform of 1, which is just c times the integral from 0 to infinity of e to the negative st dt, because our f of t is just 1, which we evaluate, we get negative cs, negative c over s times e to the negative st evaluated from 0 to infinity. So that's negative c over s, and then when we plug in infinity, that goes to 0. That's why we defined it to have an upper bound of infinity to begin with. When we plug in 0, we get a negative 1, because it's the lower bound. So c over s is the Laplace transform of c. Pretty cool. Probably the next most common one is the Laplace transform of e to the, say, at. And I did this in my last video, or at least I alluded to it. So this is the integral from 0 to infinity of e to the negative st times e to the at dt, which is the integral from 0 to infinity of, let's do e to the a minus st dt. So that's 1 over a minus s times e to the, and I'll write it as negative s minus a t d, or no dt because we already evaluated it. And this is from 0 to infinity. So 1 over a minus s times, now when we plug in infinity, again, the thing goes to 0. And then when we plug in 0, the thing becomes, well, a negative 1. It's a negative because it's the lower bound. So we get 1 over s minus a. And that's the Laplace transform of e to the at. So what I said in the last video is actually right. Now, another common one, it's going to take a little more work, is the Laplace transform of t to the n. So for example, t squared, t cubed, and so on. We're going to use this Laplace transform, and it might not be obvious the way I'm going to do it, but let me go through it here. So recall, though, that e to the x is summation from n equals 0 to infinity of x to the n over n factorial. That's the Taylor series for e to the x. So since this is true for all values of x, and if I want to use this here, I'm going to let x be equal to at. So e to the at is sigma n equals 0 to infinity of, and I'll write it like this, t to the n over n factorial times a to the n. Now, so something else that I want to do, I want to use this fact here. I know that 1 over 1 minus x is sigma n equals 0 to infinity of x to the n. Of course, for the absolute value of x less than 1. That's just the sum of the infinite converging geometric series with the first term of 1 and a common difference of x. So, if I look at this, this is similar to 1 over s minus a. This 1 over 1 minus x is similar to this 1 over s minus a. And if I want to write it in this form, I can factor out an s on the bottom, and I can get 1 over s times 1 over 1 minus a over s. And of course, for absolute value of a over s less than 1. And so now, I should get that 1 over s times 1 over 1 minus a over s, that's equal to just 1 over s times now sigma n equals 0 to infinity of, and I can write it as a over s to the n, which is, if I put the s out front into the summation, that I can write it as sigma n equals 0 to infinity of a to the n over s to the n plus 1. So, what does this tell me? It tells me that, okay, see, I know that if I were to take the Laplace transform of what I just circled, I would get the Laplace transform of this, of e to the at, which is 1 over s minus a, which I have shown to be the same as this for that condition. So what I can say then is that the Laplace transform of sigma n equals 0 to infinity of t to the n over n factorial times a to the n is sigma n equals 0 to infinity of a to the n over s to the n plus 1. Okay. So now I'm gonna pull something from Calc 3. Hopefully you follow along here. Oh, oops, my circle went. Oopsies. Well, we have the necessary stuff here. So the Laplace transform is just an integral. And so what I can do is if I have a summation in the integral And since we're assuming these functions to be continuous and all, there's a theorem. It's called, Fubini's theorem. It deals with how you can change your integrals, or when you're doing multiple integrals, how you can change your integrals around, or if you have an integral inside of if you have a summation inside of an integral, you can flip them. So what I can do by Fubini's theorem, and you can research this more if you like, is I can turn the left side of my equation into sigma n equals 0 to infinity of 1 over n factorial times the Laplace transform of t to the n times a to the n. So because a is just a number, n is varying, but so I can pull it out front of the Laplace transform, which is really just an integral, because the integral is with respect to t, and so n would be a constant with respect to t. And likewise for this a to the n as well. So I grouped it like this because what I just underlined, the Laplace transform of t to the n, is what I want to find. That's the whole point of doing this. So this is still equal to sigma n equals 0 to infinity of a to the n over s to the n plus 1. And now since these summations have the exact same bounds, and that would imply that what is being summed needs to be equal to each other. If the two summations are equal to each other, then the nth terms need to be equal to each other as well for that to happen, because the bounds are exactly the same on the sigmas. So that means that 1 over n factorial times the Laplace transform of t to the n times a to the n is a to the n over s to the n plus 1. And now I can just solve for the Laplace transform of t to the n. I can get rid of these a to the n's. And so the Laplace transform of t to the n is n factorial over s to the n plus 1. And that took a lot more work, but there it is. I think I just two more, probably the sine and the cosine, and I think that'll be it for this particular video. So let's consider the Laplace transform of the sine of bt and the Laplace transform of the cosine of bt. Now, you could do each one of these separately, and remember that this Laplace transform is just an integral. It's the integral from 0 to infinity, v to the negative st times the sine of bt dt. So b and s are just constants. And so you could do that with integration by parts. But and you could do the same thing for this one as well. But I'm going to actually knock two birds out with one stone, so to say. Let's consider the Laplace transform. This is kind of an unusual way of going about it, but let's consider the Laplace transform of e to the at. That's 1 over s minus a. Now, this is true for, actually let me use alpha because I'm going to use a in a minute. I'm going to turn this a into an alpha t, s minus alpha. So this is true for all values of alpha. So I can set alpha then to be equal to a plus bi. Why am I going complex? Because I know that there's a relationship between e, sine, and cosine in the complex numbers, right? Euler's formula. So that means that the Laplace transform of e to the alpha t is the Laplace transform of e to the a plus bi t. Actually, my bad. I don't need to, this will derive something else. Let me keep it as an a and keep it as an a. And if instead I just let a be equal to bi, the way I was going there, I would have got the Laplace transform of e to the at times the sine of bt. That's not what I would have wanted. Well, I'm going to let a be equal to bi, and so I get the Laplace transform of e to the bit, e to the bit, which is the Laplace transform of the cosine of bt plus I times the sine of bt. And that's going to be equal to 1 over s minus, now I replace this a with the ib. So 1 over s minus ib. Oops, I changed my thickness. And now if I multiply both sides, since, I don't like to be on the bottom, I like to be on the top, can multiply by s plus ib. And so I get s plus ib over s squared plus b squared. And now we play mix and match, right? Because, well, first of all, I'm going to apply the linearity and scalar properties of the Laplace transform. So that, what I just underlined, is the same thing as the Laplace transform of cosine of vt plus I, since I is a constant, times the Laplace transform of the sine of bt. This is going to be equal to this here, which I can write as s over s squared plus b squared plus I times b over s squared plus b squared. And what this really comes down to is the property of complex numbers, of equality between two complex numbers. A plus bi is equal to c plus di if and only if, if and only if a is equal to c and b is equal to d. And you're like, well, obviously, but this powerful property can be applied here, because this then must be equal to the real part. See, the real part equals the real part, and the imaginary part equals the imaginary part. What this tells me is that the Laplace transform of cosine of bt needs to be equal to s over s squared plus b squared. And the Laplace transform, that's a bad L. The Laplace transform of sine of bt needs to be equal to b over s squared plus b squared. And we just got two of them there in one stone with the complex numbers. I think that's pretty cool. And I think I'm going to leave it at that. I hope that you found this helpful, and later on I'll be actually using